Thank you. Let's get this up here. Here we go. From topology to faces. Now, this is not going to be a usual title, but let me give you some idea. Now, this talk is with the topology from Lewis Narins. And also, you're going to find out that a lot of the slides here, I guess, came from Kimberly. Kimberly doesn't know it, but we're going to have some slides in there that were in her presentation. Now, really, what is the theme? By necessity, when you run experiments, by necessity, the experiment is really local. You got that person there. They're looking at this type of a data. So it's local by nature. But what you do is you observe some mysteries. And so really what the theme of my talk is going to be is that some of these mysteries can be explained if we can find a global structure, if I can find a way of taking all of this information, the local information, and piecing it together in a global story. And so what we're going to do is talk a little bit about that. Now, when I do this, watch carefully now. Watch carefully. I'm going to ask you a question. What was the emotion of that woman? Sad.
Happy.
Happy? Okay. Choose the one you want. Choose the one you want. You want that side?
Yes.
Or do you want that side? Okay. But what you have here is, so really the question is that it's well known through the literature, et cetera, that people are going to choose one side or the other. They have a tendency of choosing one side or the other. Now, the question is can we explain that? And that we're going to come up with a possible explanation toward the end by use of some topology. But first, the issue is really a parts-whole issue, isn't it? It's how do I take this part and that part together? How do I put it together in an interpretation for the whole? And really, in that sense, it fits in quite nicely with many of the talks that we've had already, particularly yesterday. Some of the comments about connectivity, some of the parts, these various type of issues. And so what happens then is I'm going to talk a little bit now about a part-whole issue where when we take a global perspective on a part-whole issue, we end up with a different answer than we might have thought. And that's Arrow's theorem from social choice. Arrow's theorem, most of you know it, some of you do not. You'll find out what it is in a second. Arrow's theorem, what it does is it's usually described as asserting that once you have 3 or more candidates, no voting rule is fair. And namely, if you have an election, if you have Alice and Bob from yesterday morning, if Alice and Bob are running the candidates, we can expect a majority vote will give you a fair outcome. But suppose we have 3 candidates. Suppose Carol comes in. If Carol comes in, well then maybe fairness, maybe accuracy, maybe whatever you want to have, maybe it's lost. Or maybe it's the procedure I'm using that's screwing things up. So let's see remind us what Arrow's theorem says. We've got 3 or more alternatives. I'm going to just do it with 3, but 3 or more alternatives. Candidates, whatever you want. The information comes from voters' preferences, or for people in here, it comes from your data in your lab. And let's assume that the way you put it together, et cetera, that the information that you have, it's going to be complete and transitive. A better than B, B better than C means A is better than C. The outcome we want when we aggregate it, no matter what method you're using, the outcome we want is to be complete and transitive ranking. Okay, you can relax this, but it doesn't get rid of the theorem. Now all we have to do is worry about the rule. Now here's where I'm going to differ from usual interpretations of Arrow's theorem. I'm saying that what Arrow has decided, he doesn't have it in his book or anything, but what he's doing is taking the reductionist approach. What's the reductionist approach? The reductionist approach is where we have a complex problem, we divide it into parts, find the answer for each of the parts, and put them together again. And then we're done. We can go and have a glass of wine, okay? And so what did Arrow do for these problems is he said, let's find the complete transitive ranking for the alternatives by breaking the problem into pairs. And what he's going to do is, if you have 3 candidates, we're going to find what does society believe about A and B, what do they believe about A and C, and what do they believe about B and C. Reductionist, we're only allowed to use information about A and B when we're doing this. C doesn't play a role in it at all. It's a true reductionist. Second thing we do is just going to say that pairs are not constant. That for each pair you can have more than one outcome. That's all. And the third thing is that it's not determined by a single source of your data, or it's not determined by a single voter. And you can write that down more specifically, but that's all what it says. And the conclusion is that no matter how bright you are, how clever you are, you're not going to do it. It's impossible. Impossible to construct something that will always work. The importance of this particular theorem, it's that you might come up with a method for a particular election. And we see a large number of groups running around the United States today talking about how to solve the problems of the last election, win the last war. About see how this method right here would be fine. But what this says is no, that's not going to work. Your method, there will be other situations where your method will not work. Now, what happens is this has been interpreted as saying that no voting rule is fair. I don't accept that. I'm saying that really it's the methodology. I'm simply saying that what Arrow's theorem says, and here I'm going to come up to a comment that some of you might not like next, the reductionist approach is not appropriate. That is, when you're trying to find answer, do not use paired comparisons with your data or with anything else. Now, Bill did so yesterday. And Dan said, wait a minute, how come we don't get cycles? How come we don't get all kinds of difficulties, all kinds of problems? The reason is that if you go back and think about what Batchelder said yesterday, he had this cumulative distribution function, etc. He is not using the reductionist approach. He gets around the problem because he's not using the reductionist approach. He's using information about what's going on with everybody else, aggregated, but that's fine. And it is only because of that that you're able to get rid of it. But the important thing is when you're having paired comparisons by alone, be careful, folks. You can have a lot of troubles. And really this result, it's a global result. It says, I don't care what you try to do, you're going to have trouble. It's a global result, and the results are a consequence of looking at it from a global perspective rather than what happens here, what happens there. Let's take a look at another simple example. And this is a beach party on an island. And Lewis came up with a nice picture that I borrowed right there. We're going to have a party right on the beach of the island, okay? And so we have a decision theory analysis problem. Where should we have that picnic? Where should we have that party? All righty. So we can take that beach island and we can make it into a circle. And so we're going to try to find a place where to have the party on the circle. Well, there's going to be 2 people are going to go to this picnic. Want 10, fine. You can make modifications, everything goes through. And so therefore, really the choice of where to have the picnic, the input, are going to be points on a circle cross a circle or a torus. So Bob might want here, Alice might want here. So there's our inputs about where we would like to have it. And what is it that we're going to do? This means I have a mapping, a decision problem. The decision problem is that I'm going to choose what Bob and what Alice says, and then we're going to decide where to have the picnic. Seems easy. I mean, look, if we're going to have a picnic along this part right here, just choose the average of what the 2 people want. I mean, it sounds pretty easy. So let's write down some conditions. The properties, the first one is, let's assume that the function is the decision analysis function is a continuous function. In other words, if Bob wants to be here and then moves over a little bit, we don't want the answer to jump or something else like that. We want it to be continuous. That's fairly innocuous. Second thing what we want is unanimity. If Bob and Alice want to have the picnic at the same place, then that's going to be where we should have it. And these are local conditions. Notice these are local conditions, just like I was stating earlier in terms of experiments. Experiments are local conditions, and then we were talking about piecing them together. And then the next local condition type thing is really a reasonableness, Pareto or reasonableness. By this I mean that the outcome must be, that if the two choices, Bob and Alice, their choices, create the point, this is what we were just going through in the last couple of lectures, find the geodesic, the shortest distance between them, the shortest arc, and the answer should be there, somewhere on that arc. I mean, for example, look, if Bob wants to have it there, and Alice wants to have it there, we surely shouldn't have the decision state and say, let's have it there. Instead, the answer should be somewhere between Bob and Alice's choice. That's all I'm going to have. Only conditions. So the domain is a circle across a circle. So what happens, here are the local conditions, and really here is, well, on this island.
So the position on the circle
Yeah.
is P.
Yeah, excuse me, you're right, you're right. I should have put theta there. So it's the position on the island. It is the position on the beach, on the circle.
But the smallest arc is not continuous.
I beg your pardon?
The smallest arc is not continuous itself, so that's impossible.
That's right. It will not always be always defined, unique. But usually it is. Okay. But we can generalize. We can generalize that too. Now, what happens is the question is what will be the? I mean, you probably can come up with about a dozen different maps or answers for this problem.
You don't want symmetry?
No, I don't need any symmetry. Why do we need symmetry? Alice has a better choice, a better sense of where they should have it than Bob. I mean, why symmetry? I'm not going to throw symmetry. We're just going to throw that in there. And what are we going to do? The conclusion is that the only map you can have must be homotopic to a function of, oh God, what in the hell does that mean? It must be homotopic to a function of a single variable. In other words, what it really means in terms of real words is that one variable dominates. That, in terms of giving an example, it must be that one person, and that person is specified. It's actually the mapping specifies that person, whether it's intended to do so or not. Whatever mapping or whatever choice you have, it can be shown that one person dominates the decision-making process. One person will say, I want to have it here. It's not a dictator. It's homotopic to a dictator. So one person can say it's here, and we can adjust from what that person wants, what the other person can do. The other person cannot make a major decision, but it can adjust. And so homotopic means that if we reduce the amount that the other person can adjust, we end up with a function of one variable or a dictator, is what it means. Okay, everybody with me on that? Because that's important for what we're going to be talking about. And really, what causes this result is the structure of the domain. So let me go through that again. All we have is continuity, the obvious unanimity, there's nothing wrong with that, and then this reasonableness. Those are the only conditions we impose. And the consequences then must be, because I'm talking about a circle, about the global structure of what's going on. Okay. And so, and in fact, what happens, it's even more general, it's that you don't need a circle, you can have an annulus. All you need is, or you can have a tire, a car tire, or anything. All you need is something that can be deformed continuously into a circle. That it has a hole in it, that's all. You don't need anything more than that. And what it says is that immediately once you have that type of a structure, then one of the variables in the choice of function you gave me, that function will tell, if you analyze it, will tell you exactly what, which variable is the dominant one. All right, we're going to use that to go back to this problem here. The island theorem is going to explain or give us a reason why we chose one side or another. And we had different answers here. And what happens is these next several slides are absolutely wonderful. They're not mine, but they're wonderful. And I got them from, stole them from Lewis. Oh, from Kimberly. That? Expressions are universal. Happiness. Okay, or sadness. Or surprise. Or anger. Or puzzlement. Okay. So what we have is, and this really goes back to what Kimberly was talking about in the last talk, wasn't it? In terms of universal expressions are pretty much the same, and all of these type things, and so the expressions go here. And what I'm going to do next is I'm going to take another one of her slides that I stole, because what it is, if I want to be able to explain that problem, that island problem, I need a circle, don't I? I'll be darned if I don't have one. A circle in terms of the emotions. I have a circle in terms of the now, it might not be a circle. You know, in fact, when you look at some of the data and some of the literature, it's not a nice circle. It spreads out and even comes out in a different dimension and things like that. But the important thing is that you have something like a circle going around in this type of a problem. Now, a circle. All I need now are two participants, so I can get the island theorem. Well, one way is one side of the face, the other side of the face, or you could use a picture that you had in yours, essentially, in the first talk, where what happens is each eye gets information and brings it to the left into the right hemisphere, and so what we have is this type of a situation. So I've got two participants now. I've got a circle, the circle of emotions. And I've got two participants. And what I want to do on here is we have something like this. Well, annulus, that can be deformed into a circle, that could be deformed into a circle. And so really what we have now is the same setup, structural setup, that we had for the island problem. Now, I don't know how the brain works. I don't know how the brain makes these interpretations. So let's just hypothesize some of the properties what the brain does. The brain looks at this, at the pictures, and it has a continuous distortion. If we take this, you have an interpretation. If this goes up like that, it's not going to really make that much of a difference in the interpretation. So continuity is reasonably easy to accept. Second thing is unanimity. That's obvious. If both sides are the same emotion, and you see it very quickly, you've got the same emotion. So that would be your answer. So that's obvious. And also reasonableness, that, if there's somewhere, we saw those, actually, we can go back to Kimberly, where she wrote down, these are good, these are bad. Well, they're reasonable, the interpretations, all of the things are there, and you expect something to be in that arc. Now, I don't know how the brain works, or how the brain interprets these emotions. I have no idea. But it doesn't matter. With these three conditions, the mathematics says that one side must dominate, the right or the left side, must dominate in making the interpretation. It's not a question of what is that function, or how does the brain do these things, or anything else. Either one of these conditions are false, that's fine. Or what happens if they're not? Then we have an explanation by taking the local information that has been run in lots of experiments, taking the local information, and we have that indeed what happens is when you put it on terms of this structure that it's working on, which is in this case is the circles, that one side must dominate. Yeah?
Should there something implicit in this that there are no configural properties? In other words, the whole is the sum of its parts, or crosstalk between the two faces? Like I assume Bob and Alice, they make independent choices and then your model makes their decision.
That's right.
But here, you're looking at the whole face right now.
Well, now you're looking at the whole face, and I'm taking a look at the quick interpretation, the first interpretation. When you're looking at the whole face, you see that it's mixed up, and you see the both sides. Absolutely correct. But I'm asking for the first interpretation.
Will it make any difference if it's top, bottom?
Yes. Yeah, if it's top, bottom, what happens is you do see the difference. And actually, Lewis has run some experiments on that, haven't you, Lewis? Or you said you were going to. Maybe not.
We have the experiments and we have the data,
Okay, good.
but we have not looked at it.
All righty. What do you, yeah?
A brief technical question. So this theorem, does it allow for the dominant argument to switch?
No.
It should be throughout
I'm
the
gonna
domain,
get-
it should be
Yeah, that's
just left
right.
or right.
That's always one side or the other. In fact, we're going to come to a switch in the next slide, where there is a switch.
Just a basic question. This circle of Kimberley's, I presume that you can put stuff in the middle, which stops it from being that topology. You can, for instance, put a completely blank face in the middle.
Yeah, and that's a neutral face. And what happens is when you have a neutral face, blank face, neutral face in the middle, which is what she had when she had these things. What you're doing is you, when you're taking a look at the beach, the island was full too, wasn't it?
Oh, but you're not allowed to have a party here. But I'm
Yeah.
saying that perhaps here you are allowed to have a party. in the
Yeah. No, that's a possibility. Yes. And
But it doesn't work. The neutral face isn't in the middle. It's on.
it's above and above. Okay. All right. Yeah.
One side dominates in terms of F, what does it mean exactly?
Well, it means that that really left hemisphere, right hemisphere, and for the quick initial interpretation, one side will give the interpretation. Either the left side or the right side will give the initial interpretation of what is the emotion on the face.
So it's a forced choice. I mean, you're asking the subject, what do you see? All right. There's no option for them to see, say.
The whole thing.
Huh?
No option to see the whole thing because it's real short. There is an option here, but notice I just gave you just a real quick time to look at it, didn't I? So you'd have to make an interpretation.
So you have a function that maps P1 and another function that maps P2.
Beg your pardon?
When you I'm not clear about what it means from the standpoint of the function, one side must dominate.
Oh, one side must dominate. It just means that
On the circle, you know, there is some intuition, but from the viewpoint of the function F,
what it means is, let's suppose we had a function of suppose f could be written like this. Suppose it was separable in this sense. I don't have to. It can be anything you want.
I know. So there are two functions.
Yeah, and then what it says is that really what this function is it diminishes the impact of this one right here. That's what it means. Okay? So any other questions? Yes?
Yeah, I'm not sure I'm following things. We need the so why do we need the dominance?
Why is it? Oh,
Yeah, that's, I guess, what it.
let me quickly outline the idea of the proof. The idea of a proof is that I have a circle across a circle, which is a torus, a donut. Alrighty. Now what I'm going to do is I'm going to rewrite that donut. I'm going to split this open in both here and here at the North Pole. And so I'm going to take this and open it up. So this point and this point right here are the same. And I'm going to open this up, and this point are the same. And so therefore the torus can be written, the domain can be written here, except this edge is identical to this edge, and this edge is identical to that edge. Okay? Now, what happens is I have a function. I have a function over here. Here is the outcome. So I select what will be an outcome. And what I have to do now is I want to find what's its inverse set. Okay, and we had that with the Shakespeare talk this morning, the inverse image type thing. So the inverse image of this point right here, I don't know, suppose it's right here. Well, that's the same as this point right here. So now what I do is that might be what it looks like. It cannot go from here to here. I mean, you have some things to prove, but you can't go from here to here to here to here or something like that. You just can't have that. And there are a couple of things you have to prove. But once you have one of them that's this way, all the others have to be this way too. All the level sets for all the other points have to be that way. That's from the structure of the torus, from the structure of the level sets. And what happens is, if it were a straight line, then this person is what? Is a dictator. It's a dictator because it doesn't matter what the other person wants, that's going to be the level set. And so what you're doing is, really the theorem just comes from analysis of this type. So that is just a brief idea. But what it does is the structure, and really you have a hole there, and that's what's causing it. All right, so that means, again, we see the global structure answers puzzles that can be uncovered with local experiments. And what we're going to do now is, are there any other uses of the island theorem? In other words, are there any other places where I see a circle? Oh, I remember some from the last talk. Okay, what happens is center-surround type issues, where this color and this color are the same, and what happens is the surround changing colors, what happens is you have a different interpretation of what it is. So what do we have? Oh, we got the hue circle. And it can be any line as long as I can distort it into a circle. So therefore, what I have is this center, surround. The color's on there, and the idea is that I want to have a mapping that gives me an interpretation of the center. What are natural properties of this? That the function is continuous. Unanimity. If you had this, it's just one color. It's just a sheet of colors, the same color. Here, reasonableness. Okay. Whether this is true or not, if the conditions aren't true, then what happens is you have a way to go, you know where to look. And the conclusion is one region, either the center or the surround, has to dominate in a selection of the in a selection interpretation of the color that you have in the center. And what we have here is this problem right here is a little bit more complicated, because whether it is the center, the color of the center, which dominates, or the color center of the surround, it really depends on saturation. We've got another variable. Now we come to your question. We have another variable. And at times, when you use that, change that saturation, actually two variables for both center and surround. When you start playing those games, as is known, it jumps. Which one dominates? So the question is, now I have another theorem that I have to prove. F is continuous, but it has some parameters in there rather than variables. And that's where my comments about the line integrals come from, is this right here. So I got some other variables inside there. And we already know from the last talk that saturation plays a role in the interpretation on these things. And so what happens then is what happens if this function with the parameters switches where this one dominates to where this one right here dominates. You have to have, you're going to have discontinuities. And the discontinuities, the statement is how do you find the minimal types of discontinuities? And what will happen is you will end up with, the discontinuities will correspond to gray spots. And indeed, we found in a couple of articles where indeed, by playing these games, where all of a sudden gray spots come up in terms of the interpretation. And that's precisely what you will have here. The mathematics even shows what's the behavior right around the gray spots, which is what you would expect it to be. It has to be, from the mathematics, it has to have pretty much a spectrum on it. And so that's what we have here. So what we have then, as I stated, the full story on this analysis right here It's a bit more complicated because when you throw the saturation in there, you have some parameters and you have to worry about how things evolve and everything else of that type. But the important fact is really that with incredibly simple conditions, you get a very strong conclusion about the global behavior. Very simple conditions which are really defined by local behavior. What happens is if the underlying structure is there, you then all of a sudden you have that. And so hopefully what I have is gives you a flavor of what can be obtained from topology, and I keep emphasizing topology. The reason I emphasize topology, it's that all of the data and everything I've heard with the talks that I've heard in this room here, you don't have a nice circle, you don't have a nice anything else, you don't have a nice, you have an annulus or you have a couple dimensional domain or something, but you might have a hole in it or something else. And what happens is with topology, it allows you to compact things and to try to find out for a whole category of things what goes right and what goes wrong. And then with the topological type things, what you're able to do then is you're able to obtain information about the global behavior, and the global behavior gives us information that we discovered with local information, with experiments, but we didn't have an explanation for it. And so this is what helps us in that. Yes?
Just if there's this parameter, and let's say parameter taken as an argument, the function is also continuous at that parameter.
Yeah.
And if, depending on the value of the parameter, the dominant argument can switch.
Yeah.
What happens at the boundary then? Is function becomes constant, or?
No, we're not going to have it. Yeah, I haven't looked at anything like that. I've just looked at the possibility if I have f of lambda here, or f of s for saturation.
Yeah, but let's say at lambda 1, P1 dominates, and at lambda 2, P2 dominates.
That's
So
right.
between lambda 1 and lambda 2, there is a point.
There is a
Where
point.
there is a switch.
There's
and
a
something
switch.
should be happened there.
That's the discontinuity that I was talking about a few seconds ago. At the switch, in between the two, P1 and P2, where they dominate, there's going to be a point. Actually, you're going to have several of them. What you want to do is you want to find the minimal kinds of discontinuities you can have. And there will be a discontinuity. And what's a discontinuity? A discontinuity is where I'm not getting all of the colors. And that comes out in being gray. And that is exactly what has been found in experiments.
I should have listened to you instead of thinking.
Yeah.
Don't we have a similar discontinuity even in the phase where maybe the lips, up going up or down, and then there's this one point when you just make the switch, this one neutral. I mean, don't we actually just look at the lips, position of the lip happy or sad? And
Well, that's fine. If you have something, then you have a discontinuity. Or what happens is, see what happens is, let's take a look at what the theorem says. The theorem says that if these conditions, which everyone would normally say are true, hold, then there's the consequence. If the consequence is not observed in the lab, or you can find places where it isn't hold, then you know immediately that there's very, very little to look at. There's continuity, maybe that is what's fault, or maybe it's this one right here. This one right here is surely true. But one of these two, and you now know what to focus on to try to find out what's correct and what's not correct. And so that's really the power of it. And this is where, if you have a couple of circles, I talk about a circle, but what happens is you can have the domains where circles are tied together. Where would you get something like that? Well, I don't know, suppose in a location problem. I'm trying to find a place to locate on this square, but here is a mountain and over here's a lake. Okay, well you can deform that to a circle and a circle. And if that's your domain, that's fine, the theorem still holds. Higher dimensions, you get spheres, theorem still holds. More people, theorem still holds. Throw whatever you want, theorem still holds. And it goes there, yes?
In high dimensions, are those discontinuities similar to a saddle point?
No, the saddle point, Yeah, it could have a saddle point. I haven't really looked at the discontinuities in higher dimensions, but it probably will have somewhat of a saddle point, splitting of a saddle point type behavior. It does have something similar to that when I'm looking at the parameter here and I'm going from where one dominates to where the other dominates. I do get singularities of that type, and that's why I get all the colors that are right around it and things like this. You can get the properties, Jack.
I'm having trouble understanding one function must dominate one. Can you give an example of a solution where one wouldn't dominate? Like,
sure.
It's kind of like
sure. If I'll give you an example on the line. See, on the line, this theorem does not hold, because a line cannot be deformed into a circle. And so where is something that doesn't dominate? You want to be here, I want to be here, and we're going to choose the average. No variable dominates. Yeah.
But if they start discussing, they may change the shape of the circle.
That doesn't matter.
Yes, it does.
Not if, as long as it's still a circle.
Because the path is going to change.
All right, if we start talking and we have something like this instead of a circle, it doesn't matter, the theorem holds.
I know, but the shortest path between two
Oh,
points is
that
changing.
doesn't matter. If I do this, have it like this, that breaks down into this statement right here, and the theorem still holds. So it really doesn't matter.
No, but the path along the circle may be shorter.
Well, sure, it might be shorter, but that doesn't matter. This has nothing to do with distances at all. Just topology, so it has nothing to do with distances. And in fact, if we have a shortcut across the island or something, we're actually pulling these 2 points together. And so really what happens, instead of being a circle cross a circle, I have a circle cross where the path connects in here.
I'm talking about
The arc?
assumption 3.
Yeah, don't worry about the arc. Really what I write down the arc because that's easier to understand. But arc, you can replace arc with the following. You can say that, here I have a circle, and then what you do is you tell me, maybe we'll have Kimberly say that, well, you know, Don, when we're looking at people in such and such an island or something like that, it's not that distance. All right, we can say that it will be some point either in here or in here. You choose the size that you want, and it doesn't matter, the length doesn't matter. That's just...
Then it can be deformed.
It can be deformed into whatever you want, yeah. And I can get the same thing. Brian.
Inabar was telling me over snacks that
Yeah.
the problem with the philosophers treating the Soriades paradox is that they don't think of the responses as probabilistic. So suppose our decision rule gives us a probability distribution.
Sure.
Then things change a little bit.
They change, yeah. They change, and you can, but depending on conditions that you pose on the probability now, that means I have to throw another condition on here. And depending on the conditions you pose on what's the underlying probability, that it's really in some neighborhood, here is a point, and we're taking a look at the support, region of support, theorem still holds. Because if it has this reasonably small region of support, you can just collapse that, can't you? And so even if you have a probability function on there with a region, a small region of support, so in other words, with likelihood I'm going to be here, maybe a little bit here, a little bit here, here, but I'm definitely not going to be around there. You know, so I have a region of support like that, so that can be collapsed. The same theorem holds. So the theorem actually holds in a lot of places.
If the guys were exactly opposite positions and they decided to flip a coin, then...
Yeah, well then you're changing the rules of the game. Yeah, then you're changing the rules of the game, yeah. Yeah.
So, in all of the decision mechanisms I'm imagining here, it seems like you have some perverse motion of the decision. Like sometimes, so you have the dominant guy, and as the second guy moves around, he'll pull it in one direction, but at some point it'll stop being pulled in that direction. And as that guy continues in the same direction, his motion will move in the other direction. Is that a property that you're going to find with all of these mechanisms, or is that just...
No, this just happens to be for this one. The proof of this, I have, a proof which uses something in algebraic topology called index theorems. And I'm not even going to try to define what they are, but they're just spinnings and things like this. And the analytic proof which I came up with is far more informative about what can happen and why it happens and how far you can be off, et cetera, on that. Okay? Really, I think my next slide was really my last one, and I just going to say thank you on that. And any last questions?
So what prevents us from living on a filled circle? I understand that it holds perfectly beautifully on the circle, right? But if you fill this with gray in the middle,
Yeah.
then if the two guys are in the
Then
opposite
what
sides,
happens is you can
choose
just use
gray.
the average or something like that.
You choose gray, right?
Yeah, yeah.
And so all these beautiful results go away, and you just have a boring, you know, you can just take the average, exactly like on this line.
Yeah.
But because we see all these switchings, it means that our space is a circle. So what prevents us from choosing gray? Why is it
What prevents us from choosing
gray?
the middle? Oh, in the island one, you sure don't want to have your picnic there. Yeah.
It's a color space.
Oh, color space. And what happens is that it'll be totally gray if you have it in the center there.
Right. So when you see these colors, what prevents us from operating on this filled circle?
Then you see what you have is what you're erasing there is an application of the theorem, isn't it? It is you're raising the question. No, let me finish. You're raising the question that perhaps the domain's shape right here changes, and by the domain shape changing to be filled in so that it's not contractible, you're arguing that that's something that we should try to look at and to try to use as part of the interpretation, which hasn't been looked at, and that's fine.
But that's what you would say is at the discontinuity, right?
That would be the discontinuity thing. Yeah.
The converse is not necessarily true.
No.
So maybe this one.
Yeah, it's.
Well, this is one of your assumptions. Assumption 0 is that your space is a circle. Right?
Well,
you have four assumptions.
deformable to a circle. Deformable to a
Right,
circle.
topological circle.
Yeah.
So these are your four assumptions, and I don't doubt at all your theorem, right? But
that's
when we
good.
have our color vision, right? Why is it that our space is a circle?
Have you? Do we know that?
I'm asking. I don't think it is.
Well, I mean, you see, the point I'm trying to get across is that the questions you're raising to try to avoid the theorem are exactly what we would hope to get from the theorem, isn't it? Asking new types of questions, right?
Let me add something about
Okay.
Don said we got a gray. That gray is really in a new dimension that's not in the CIE space. So what is going on here is, you didn't quite say it completely. Either you are discontinuous, or you keep continuity, but you have to go in the new dimension.
No, not even then, because now you get a sphere. And if you have a sphere, what happens is the same theorem holds.
No, but I mean, because the gray.
Well, see, but what you're doing, yeah, but what you're doing is very nice. It's saying that somehow or another, what you're saying, let's listen to what you're saying. You're saying that when I'm looking at colors over here, that my mind is using information here. Right. I don't think we know that, do we?
Well, we don't know
No, but that's the type of a question that would have to be investigated to try to get you to prove your point. And that's a type of question that has never been looked at before, has it? Yeah.
Just interject very quickly. We discussed those color spaces, in relation to your talk, and some of them actually do not have anything inside sphere.
How about gray?
Gray is on the sphere.
Yeah, it's on the top, but yeah.
Yes.
No, that's white.
Higher dimension.
Well, it's white, yeah, and
And black.
in
And this is
on the four-dimensional sphere, on the surface of four-dimensional. So there is only, those things that have this, ball filled in, they are not good models of
I
color.
see. So I'm.
Really what happens also is you're getting that saturation variable inside there. Yeah, is what you're getting inside there. Now you're getting down to, but you see if what people have and the experiments are in here, you're not going to, because, well, you're getting to the discontinuity is what you're getting to, that I described earlier. Further. Okay, yes?
I just wanted to comment. I really love this use of topology to solve to look at this issue, and I wonder if like the functionality, the lateralization of functionality in the human brain is because some of the problems that are being solved can map in some way to sphere topology or circle topology like this. So one side of the brain or the other must assume the dominant functionality for that particular problem it's trying to solve.
And we know that there is this dominant functionality of the brain, one side or the other. And what this does is, and what we do is we get, and what this is giving us is a possible, I'm not saying it's the explanation, it gives us a possible explanation, a possible insight that really, that function, what's actually happening, and that's the important part here. What's actually happening, what's that choice of F, doesn't matter. It's just these local conditions are all that matter, and you get this strong conclusion out of it as a consequence, which is somewhat surprising on that. Yeah. Any other last, yeah?
I wanted to ask you to speculate about something that goes a bit beyond what you discussed. Sometimes our perceptions alternate. So if I look at a Necker cube, sometimes one face is in front, sometimes another. But I didn't notice that happening with that asymmetric face. And do you have any ideas based on your analysis what might be?
Not using these type of techniques, no. Not with these type of techniques. But there's...
Maybe the Necker cube is the gray spot where it could be either or, and that's what, it's right on that edge where one interpretation switches to the other. Maybe if the cube is slightly rotated instead of being dead on, you'll tend to favor one interpretation or another is possible.
So, I mean, that's something I hadn't thought of at all, and so I think I don't think I should speculate anymore. Any other last comments or questions anyone had?
Discontinuity is all alike with respect to that theorem. In other words, small discontinuity, tiny discontinuity.
No, but these are big ones. These are big ones. The discontinuities are big.
But I mean, let me introduce into one like small discontinuity.
Yeah.
Would it matter that they are small? It will still
hold, because I could have a smooth approximation using usual type of mathematics. Yeah, and so with mathematics I can take a smooth approximation, let the approximation go in the limit, and what happens is you have that type of a condition. So the discontinuities, and that's an excellent question that he asked you about the discontinuities. They've got to be fairly major if to break on these things, and that's surprising. Yeah.
I think I could prove that you have to have perverse motion unless you're in the dictator case in these decision mechanisms, particularly because you have a topology point in the middle here. If you lay out the torus...
There's no fixed points in here at all.
Well, no, you have to have a fixed point in the middle. Like I said, the center line has to be a fixed point because you're switching which arc is the shortest arc in the middle. That's when the guy spins around to the other side.
No, what happens where the discontinuity comes in.
Pardon me, there have to be three fixed points. You have the top and the bottom have to be the same thing.
Yep.
And then there has to be something in between those
Yep.
two that is also the same thing. I guess it doesn't have to be in the middle.
No, it doesn't have to be. Remember, whether it's left and what's right here doesn't matter. You can slide it.
So you can go to the left of whatever that fixed point in the middle is initially, but then you have to cross that fixed point, and you can never go left of that vertical line at that point because you're in the other arc.
Yeah.
And if you do, you're going to be in the wrong arc. You're going to be in the wide part of the circle. So you always the lines can S a little bit. You always, if you S out, you always have to S back into that middle point.
And you have to. There has to be a dropping of certain points. Yes. And you have to. And that's you got this essential idea of some of the structure of the discontinuity, but it's a little bit more complicated. But you have the intuition, correct intuition.
The point is that when you move out, you're going to always have to move back to get to that point. So you always have this opposite.
With continuity, you have to.
Yes,
yeah,
continuity.
That's why you have a discontinuity, why it's going to be large, yes.
It seems to me this is similar to you're saying there is a non-uniqueness of comparison operation on set, right?
Well, to what?
There is comparison relation is not unique on this set, basically.
Yeah, probably related.
And then we have to decide to have multiple possibilities of, if you have, for example, A and B, trying to compare A and B, A plus some C equal to B, and we have multiple possibilities for C, and we're trying to decide based on which, what is the choice for C, but then we actually come back to the same issue, that we don't have a comparison operation for a C.
Well, you know, what we normally think is if we're doing paired comparisons, and you're getting a little bit back to that, we think when we have paired comparisons that the relevant information about A and B is how A and B are ranked. I mean, that's the way we use paired comparisons. And in fact, we now know that there is a web that connects all possible paired comparisons, or that if you don't take into account that web, which is what Bill does actually by aggregating, by looking at the cumulative distribution function. If you don't look, and this is going back to what you're saying, if you don't get rid of that, that troublemaking aspect, you are going to have cycles, you're going to have troubles. And these theorems right here have something similar, a similar effect to them too. Not quite, but the same mathematical type effect. Okay, any others? Thank you.